Assalamualaikum. Welcome everyone. We'll start the workshop right now. I just want you to know that this workshop is kind of very important for the next venture that we're going to do in November. We're going to have a competition. You're going to receive real time, like real data for business, and you're going to analyze these data, mostly visualize it. Probably you will need to use also the clustering methods to understand customers' interactions and like hidden patterns behind data. Inshallah, Dr. Mujahid will teach you more about this. I'd like to welcome Dr. Mujahid. Thank him very much for his time. Dr. Mujahid has taught me personally at KPPM. He's one of the best I've seen regarding like explaining topics in data analysis and optimization and mathematics. So today we'll get very technical. And I want you to leverage this opportunity to really understand the science behind the methods so that like most people can code this using a scalar, right? But the advantage you'll get here, you'll know exactly why things happen in that way. So you can also understand deeper topics in clustering, and you can even try to understand when do you use clustering and when do you not need to use it. And also it applies for other types of data analysis like PCA and PPA. It's all like connected to each other. So when you understand the science behind it, you will have a complete overview of what to do in terms of analysis. Please, I want you to give a warm welcome to Dr. Mujahid. Thank you very much, Dr. And you can begin.
Assalamu alaikum. Thank you guys for inviting me, and I thank Dr. Lila also for inviting me here. Today I'm going to present something about clustering. Clustering is one of the important methods in data analysis. And today we are going to start from scratch, something from very basic, and we try to come to a bit medium level, not to the high level, but something at the medium level. This is the outline of my talk. I'm going to start with an example about clustering. So I would like to present an example such that we understand what clustering is and why it is important in general. Imagine that we would like to buy something from a toy store, like Toys R Us. You went to the toy store and picked the toy and put it. That's it. Let us say you went in the toy store and you found something like this. Okay? These are the toys and you have to buy one of these. Now imagine how difficult it would be to pick that particular toy and then buy it from the shop. Okay? If the things were organized, for example, let us say it was something like this, then it would have been a bit easier, right? So picking a toy from here, where all the toys are jumbled, is much more difficult than picking a toy from here. So here, what's the main advantage here compared to this scenario? Here we have things that are grouped. Here we have things that are grouped for some reason. And this grouping actually made us easy to pick the item. Okay? Now, of course, this scenario is not very related to clustering, but it will give you a sense of why grouping is important. Well, this could not be a scenario related to most of you, but how about this? And of course, these guys are not doing any cluster. The way they are grouping these things is just by looking at the items and then they know what those items are, they are just grouping. Okay? But I believe most of you use this. Most of you use this tool. It's a search engine, very well search engine. And if you type in something in here, so usually you type something in here, and then it has a button to search something, and it gives you so many things. The interesting point here is, if you pay attention here, you see that it gives you something like this. It gives you something like this. Okay? It gives you so many results, which is itself astonishing to get something of this much amount for your keyword. Not only this, but also you can see that it does it very fast. So what the search engine is doing, it's not searching everything one by one. The search engine roughly has a cluster of web pages. Maybe a page has a thing called page rank, and based on the page rank, they know what this page is about. And they already did some cluster. The moment you type the word, it looks for the closest or the nearby cluster, and then gives you all the list. So companies like Google and others that are in search engine business, they are doing this clustering behind. Not everything is related to clustering, but there are a huge you can say applications of clustering. Now, other challenge here is when you do the clustering, you don't see the items. For example, when the search engine is doing the clustering, it doesn't know what's inside the web page. All he knows is what is the page rank. And using the page rank is doing the clustering. The other important thing is these items are unknown. Maybe every now and then you have a new web page, and based on that web page will be getting a page rank. And then it will be part of the linkage or cluster. So these are the two things that are going to make this problem very difficult. Without clustering, the search engines will for sure fail. Now let us see where this clustering stands with respect to machine learning. Machine learning is a big area itself, and it has two big branches, supervised and unsupervised. In the unsupervised learning, you have clustering. And to be frank, clustering is the only method applicable to unsupervised. There are many authors, there are many researchers who would claim that unsupervised learning is nothing but cluster. So they are synonymous. There is nothing new in unsupervised learning except cluster. Well, in supervised learning, you have many things. You have classification, you have regression, you have signal separation. You have many things in here. But when it comes to unsupervised learning, it is only cluster. Now, there are two main types of application for clustering. Some of the application of clustering are related to the groups. The groups are something important and the applications are based upon the groups. Whereas some of the applications are whatever is the remaining of the groups. So once you group the data, there is something that's remaining. And based on that remaining, you have some applications. These are some of the popular applications for groupings. The most common one is market segmentation. What's the idea here? The idea here is there's a company who would like to launch a product or at least study the market. And in the market, there are so many customers. So they would like to group the customers such that they can identify certain features, certain characteristics from the customers that they could exploit later in order to sell their product. The other area is image segmentation. You have data that is coming in the form of images. And what we do is we take these images and convert it to something called segments of the image. This segment basically tells you what are the major colors or major segments of the image. Using this, you can do some data analysis with the images. Then you have search engines. I started with this example. Of course, search engines used a lot, but clustering is the main, you can say, backbone of that. And then you have the social networks. Nowadays, with the advance of social networks, you can see people are connected very highly using social networks than in person. Okay? So sometimes there are certain companies who would like to know what are the groups of the social network. For example, let's say they would like to launch a product, they would like to sell a particular item. Then they will see who are the buyers, and then they will see who are the related persons to this buyer, and they will target those buyers. So there is a lot of clustering going on in the social networks. And then you have this online maps. Every now and then, if you are driving, or also sometimes in general, you would like to use GPS, the maps, and travel around. Those maps they have a lot of information, and you try to group those information again using some clustering methods. And last but not the least, you have this language processing. The main idea in the language processing is you have something written. For example, you have a script written by hand, maybe in Arabic, maybe in English, maybe in any language. Or maybe the old book, all the old literature is all about handwritten, okay? Handwritten scripture. Now, in this digital world, you would like to convert the handwritten text to something digital. And this idea is a part of language processing. And clustering is heavily used in language processing. The idea is to convert the text into something recognized by the computer. Okay. Now go to the other part of the applications. These applications are based on what is remaining. Once you do the clustering, there is something that are remaining. And based on this, you have applications. And the most important application here is anomaly detection. So you have the data, you cluster everything in the data. And then there are certain points that you are unable to cluster. These small number of points are called as outliers or noise or nothing but anomaly. So they show something different from the majority. And this something different from the majority might help you to do lots of analysis. For example, fake news. Nowadays you get news from WhatsApp and here and there, and some users are very far from reality. So how to identify this kind of, you can see Facebook is also facing with the difficulty of stopping the fake news. So one of the ways is to do the clustering and identify the anomalies, and those anomalies will be nothing but the fake news. The other interesting application is the spam filtering. Every now and then you get some email like you want something, or you are invited to something. Okay, those emails usually, very rarely they are real, but most of them they are spam. And some of the spam engines they use clustering to catch those spam emails. So those are the, you can say, the majority of the applications that you can have for data clustering. So now let us come to the definition of clustering, what actually clustering means. Basically, clustering is grouping of objects. You have different objects and you are going to group them. But not any group. There is some property, some characteristic that should be satisfied. And these are the two properties or characteristics that should be satisfied. The first one is objects or data points is the same one. Objects, they belong to the same group, then they should be very similar. And if they belong to the different group, then they should be dissimilar. So you cannot just randomly group them, you have to group them based on these two reasons. In the same group, they should be similar. In the different groups, if you pick two items from different groups, they should be dissimilar. The challenge in clustering is this is a learning by observation. So it is a tendency. You can also agree with this. You can also try to think about this. Sometimes learning by observation is very challenging, whereas learning by examples is very easy. You might want to study for exam or study for some new topic. You will realize that once you look at a couple of examples, you will get the idea, and then you will understand the topic very easily. But if you have to learn by observation, so there are no examples just here, and you have to learn by observation, then it will become a bit challenging. And clustering is exactly the same. If you have classification, then it is by examples. You have classes, and based on the classes, you can learn the classifier. But not with the clustering. Clustering has no classes. Everything is with the data, and you have to use the data and come up with the cluster. So that's the challenge in the clustering algorithm. So we'll start with the basic mathematical model that we can have for clustering. Now, data analysis, as you can see, is an area where people from different areas jump in. For example, most of you are from computer science, maybe from electrical engineering, maybe from business, maybe from, I'm not sure if you're from industrial, but you have people from different areas jumping into the data science. And then everybody has a part in data science. So you can imagine data science like a product, like similar to a car. So to manufacture a car, you need mechanical engineer, you need electrical engineer, and you need many more. Okay? Same thing with the data analysis. To build or come up with an algorithm, you need people from different areas. And among those areas, optimization or operational research, optimization is part of operational research, is one of the main areas. Actually, optimization is the main engine of data analysis. Pick any method in the data analysis or try to think about any method that you know in data analysis, you will find that somewhere inside you are minimizing or maximizing something. Either minimizing square error or maximizing likelihood or minimizing absolute error. There is always some minimization or maximization going on. From the beginning of the data analysis, there is optimization going on. But surprisingly, the field of optimization, it is emerging on a parallel track, and very many people realize the power of optimization. So through this mathematical modeling, I'm just trying to show that you can, if you are into optimization, can do much more better than the conventional approaches. So let me describe you what this mathematical model is about. The mathematical model is trying to minimize certain objectives. If you haven't seen a mathematical model before, or if it is the first time, let me just give you what's happening here. In a mathematical model, you are trying to minimize or maximize something, and then you have certain restrictions or certain constraints. Usually, it's written like this. The objective will be written at the top, and then all the constraints at the bottom. Now, here, what we are trying to do, we are trying to group the objects using the same characteristics, these two characteristics. So for that, I'm going to define a variable. And this variable is something that is unknown. This is the thing that I would like to find. So this variable is defined like this, xic, where I and c are the indices, is equal to 1 if data point I is grouped in cluster C and 0 otherwise. Okay? So that is how this variable is defined. Now using this variable, you can give this constraint. For example, for any data point that I pick, it must be belonging to exactly one cluster. So this is a constraint that you can relax later. For example, if you are in fuzzy clustering, then this is not needed. You can have a data point in more than one class. But to begin with, we have a constraint that says every data point should belong to one class. And this is most of the partitioning type of clustering do this. And then if you have a cluster, you would like to have at least one point in it. Of course, if you have a cluster with one point, then most probably it is a noise. Okay? Otherwise, you'd like to have more than one point. So these are the main requirements that you have for the constraint side. Now, what about the objective? The objective is defined like this. If point I and j, if both of them belong to the same cluster, then you would like to minimize the dissimilarity. So if there is a dissimilarity you would like to minimize. And that dissimilarity between points is captured by some function u. By some function u. And then on the other side, because it's minus and you're trying to minimize, it is like you're trying to maximize. To minimize is minus, and then you're going to maximize. And what are you trying to maximize? You're saying if I and j, if I doesn't belong to the same cluster as j, then maximize some dissimilarity. And that dissimilarity is captured by function theta. And that's it. This is the basic mathematical model that can be applied to any partitioning type of clustering algorithms. Any doubts here? Anybody would like to ask
Any questions? Any questions here? It's only going to get deeper. Okay, so you have to understand. Okay. Just one question.
The mu stands for what?
The mu is a similarity measure. For example, a distance measure could be a similarity measure. So two data points are similar, then the distance between them should be 0. And if it is not, then we would like to throw them at another person. Theta? Yeah, it is a dissimilarity measure. If two data points are very dissimilar, the value should be 0.
Any other question?
Now, if you pick any clustering method, this is what is going to happen. They will either skip this one and they will just try to focus on this, which is to maximize, minimize the difference between a cluster. Okay? Or you'll find some clustering method that are going to look at both. The definition of mu and theta, it can change, and based on this, you will have different clustering measures. For example, the K-means method that you are going to learn today, it is going to take distance as a measure of dissimilarity. But there are many more methods. You have density, you have other methods as well. You can use them and it will become a different method altogether. Now, before we come to K-means clustering, let me tell you something. Clustering can be done just by looking. You don't have to know any algorithm. You don't have to know any algorithm. You can do clustering just by looking at things. Our brain has that power to do the clustering automatically. Maybe from our childhood we are doing this, but we never realize it is clustered. For example, let me show you some pictures. Can you tell me what are the groups in the first picture? Can you see there are 4 different types of groups? The picture 1. How about picture 2? Yes? How about third picture? Can you see 2 groups? It's also the same. If you look at other pictures, you will see the same. So you haven't, maybe you know something about clustering, but let's say this is the first time. So without even looking at those methods, you know that our brain is doing that and telling you that those are different clusters. Why they are different? Because maybe they are close related, maybe they are following a pattern. Maybe they have some pattern and things like that. If you can do this without seeing, then you are building a clustering algorithm. Here our eyes is helping us to see this, but human beings have a limitation. We cannot see beyond 3 dimensions. So if I give you something in 5th dimension, data point with 5 elements, you cannot see it, that's it. And you cannot do this. But if you can see it, you can do the clustering. So clustering is something in higher dimensions. And if you can come up with an algorithm that can do exactly what your brain is doing just now, then you are building an excellent clustering algorithm. And all the algorithms are based on this concept. Try to imitate what your brain is trying to do. That's why that's a part of machine learning. Okay? So here are the clusterings for the same data. Of course, there are some noise that I added to the
If I may just ask, can anyone imagine a data point with different or multi-dimensional data point? Can you give us an example of something you cannot visualize in terms of dimensions? Like, why don't we just graph it and see? Like, why aren't all data points like that? Like, for example, you, the attendee, you have different dimensions in you, right? So, your height and wealth, let's say, weight, education, background, you have different dimensions. You cannot visualize it in one graph. But I can cluster you. If I know each one of you, I can group you in clusters, right? By just talking to you and understanding. But if you have like 1 million students, you cannot do this by your brain. You have to use an algorithm. This is the point of this workshop, right?
Now let us begin with the K-means algorithm. K-means algorithm is the oldest and probably this is the only algorithm many people know about clustering. So whenever you say to somebody clustering, by default they might assume K-means. Not with all, but maybe there are few people here, or not here but in general, who by clustering means it's only K-means. But that's not the case. Okay? And here we are going to see what K-means is all about. So this is the mathematical model of K-means algorithm. What is the change here from the basic model? In K-means, you are not interested to know if you have two data points from different clusters, whether they are dissimilar or not. You are roughly ignoring it. But what you're trying to do is you're trying to come up with a cluster center. You're trying to come up with a new concept. What is it? It's a cluster center. So you're saying that all the points in the cluster center can now be summarized by one single point. And that one single point is nothing but a cluster center. And then what you're trying to do, you're trying to say that if the point belongs to the cluster, it should be closer to the cluster. That's a very simple, very basic idea. Okay? Even maybe now, if teachers in high school, they will immediately catch this. That if you have a point, if you have a cluster center, and if the point belongs to the cluster, then the point should be closer to the cluster center. So you're trying to just minimize the Euclidean distance. You know this distance? Have you seen this distance before? This is also called as norm 2, and the technical name is Euclidean distance. Of course, the square of the distance, you also have the under root, which you are just ignoring that. And the same constraints like before. Now, this problem, although you have the mathematical formulation, this is very challenging. This is very difficult to solve. Why? Because this is a nonlinear problem. Here you have product of variables, and then you have a nonlinear function. So everything together makes it highly nonlinear. And if you know, if you are from optimization background, you will know that solving a nonlinear integer problem is the most challenging problem. So how somebody thought to solve it? Well, he said, let me approximate the method. Let me approximate a couple of things. What is approximation? That approximation is what K means. So what will happen is, you assume some values for x, you solve the problem, and get the values for GC cluster center. And then, given the values of GC, you solve for x. So you do it iteratively. You do it iteratively. And in one iteration, variable will be cluster center, and in the other iteration, variable will be x, assignment variable. So you do this iteratively, hoping that you will find a solution of this problem. And this will never happen. Unless the clusters are very obvious, they are well separated and nice circular shape, this will never happen. So if you use clustering and the clusters are not circular or spherical in shape and not well separated, you will never get the best solution. But yes, still it is a practical solution. Let me show it let me show you how it's done pictorially. Imagine you have some data points. Here you have different data points. Although I made them in different colors and shape, but let us say we don't know all these colors and shape. They are just some data points. Let us randomly pick 3 cluster centers. Some 3 points in this 2-dimensional space. Now, how to pick 3, or how did I come to know 3? Well, I didn't pick this, no, I actually cheated. Here I have 3 groups, I'm just selecting 3. But in reality, selecting K, or the number of clusters, is the main, because it's the first main question. So if you're using Cambridge algorithm, the first thing you should think of is what is the value of K? Where K stands for number of clusters that you're going to find. This K, that K is the same. Okay. So here I am doing the small, you can say cheating, and I'm just saying let me pick 3 points, X, Y, Z as my cluster center. Not only that, I'm making lots of assumptions. I'm picking it in a way that X is very close to this, Y is very close to this, and Z is very close to this. So I'm making my life easy by presenting something simple. But when you try to solve a real problem, you have no clue of what these points are, you have no clue of how many clusters are. And then you are going to find the positions, not only number, the positions of those cluster centers. So you can imagine how complicated the things will get. Now, once I have those random clusters, I'm denoting those by letter X, Y, and Z. I'm going to assign those points to the clusters. I'm going to assign them by some distance measures. For example, I'll take this point, and then I calculate the distance from this point to all the cluster centers. And the one that is closest to me, I will be part of that cluster. For example, here this point is closest to X. So now I'm going to assign this point to cluster which has center X. Similarly, I will repeat it for all the points. So it's a loop. It's a loop. The program is a loop that will go over all the points and try to calculate the distance from the point to the cluster centers, and then assign the point to the cluster center. Now let me show you how the assignment is done. Because I'm using the Euclidean distance, this is how the assignment will be done. Let me just take only 2 cluster centers. Cluster center X and Z. Then, because of the Euclidean distance, if you change the distance, this decision will change. So because of the Euclidean distance, you will see that all the points on this side of X will have lesser distance to X compared to Z. Pick any point on this side, you will say that this is closer to X than Z. Similarly, any point on this side will be closer to Z than compared to X. So that's a decision boundary that's popping up by default because of the quadrant, because of the Euclidean norm. Otherwise, if you pick any other norm like absolute norm, it will be slightly distorted. Same thing with X and Y. So altogether, this is what will happen. X with Y and Z together will come to the conclusion that these points belongs to cluster center with X. Same thing with Y and Z. Okay? And that's the first iteration, where you are given some cluster centers, you found the assignment. So given variable G, you find variable X. The next step will be, now I'm taking this as my cluster, and then I'm trying to find what is the cluster center. For example, for these stars, if I want to find a center, where will it be? Where do you think the center of these stars will be? Somewhere here or very far? Somewhere inside, right? So how to find the center is also a question. Usually you use mean. You know there is average, which is nothing but mean. And then you have median, then you have mode. If you use mean as your cluster center, then what you get is the name K means. So you have K, and for those that are getting the means. The mean of these stars will be somewhere here. The mean of those will be there, and the mean of this will be there. So this is one, you can say 1.5 iteration of your algorithm. And then you repeat it. Now you have new cluster centers. Now you do the new assignment and repeat the process. Until when? Until some calculation criteria is met. Maybe you have a number of iterations. Maybe you want to run it for half an hour or 1,000 iterations. Or maybe there is something, a measure that you have, and based on that value of measure, you are stopping. There could be many reasons why you stop the algorithm. And in the end, what you get is some cluster. And this is nothing but the K means cluster. Any doubts? Any questions? Yeah. So that's a very good question. And you see everything in the red color that are highlighted here are research problems. Still, you can find papers that are talking about how to find K. There are some ways, and you will see some simple ways and basic ways. But to find it in the best way, still unknown. There are many papers you can find even after Google. You'll find some paper in maybe 2018 or 19 talking about how to find K in tables. So everything in the red color that I mentioned is most probably a thing of for research. Somebody can think about instead of initializing with random, can I come up with something better? And then you have the scale use plus plus. Somebody can think about why to use Euclidean distance. You know Euclidean distance is not the best. If there is any noise or liar, it will spoil everything. So you can come up with a different criteria. The mean value itself, instead of using the mean, you could use median. And then if you use median, what you have is scale methods, a different class of algorithm altogether. And you know, and the termination criteria. We'll see some of the measures later on to find the termination criteria. So this is more or less all the basics that we have for k-means algorithm. Other question?
Please give us an example of definition criteria.
The most simple one is just number of iterations. After 1000 iterations, I will stop.
If there are other
There are some, and maybe while we proceed, I will show you some of the measures. Any other question, guys? So now some of the issues regarding the algorithm itself. Of course, these are the areas for improvement, but the algorithm itself has these two issues. Sometimes it might take forever for the algorithm to come up with a stable cluster. This is one of the issues, main issues for k-means. And then when you are able to terminate the algorithm, then you will find some clusters, and let us say you can draw it. And then you draw those clusters and you'll find they are completely different. They are completely different. And we'll see this by an example. But when we start to work, we'll see this. So these are the two main issues for the algorithm itself. And then these are the things that I highlighted in red color. I just summarized it here. So if you are interested to use k-mean or do some research in k-mean, probably these are the areas that you should try to think of improving. And then finally, maybe something about the termination criteria. What we have is some measures for clustering. How good the clustering is can be captured by some measures. And some of the well-known measures are here. Some of the measures are coming as external measures, some of them are coming as internal measures. External measures are hypothetical. Usually for clustering, we start by saying that we don't know what are the class labels, or we say we don't know what the data, what class data belongs to. If you know, and if you know those classes, then you can use the external measures. So it's like starting with something and then coming to the same reasoning at the end, which is not the best. But still, people try to use it, especially if you build a new algorithm and you know what are the classes. You would like to see if your algorithm is doing the right thing or not. Then you can use these measures, and all those measures are called as external measures. The popular ones are here: rand index and adjusted rand index. I'm not going to go over this because I'm not going to use this, but these are something that you can use. But let us say you have no idea, no information about the class is. Then you go with the internal measures. And some of the well-known are Shilomite index and then SDVW. And there are many more actually, but while I'm writing, I think I skipped over. What is nice about these measures is they give you a mechanism to look at possible ways to build the algorithm. Actually, these measures are going to, you can say, show us the path to come up with a better and better algorithm. So So if somebody can come up with a better internal measure, then he actually started a new class of clustering algorithms. I'm going to just cover one of this method, the Sherrod index, and then we'll go to the program. Now, all the internal measures are based on these two concepts, compactness and separation. These two concepts are actually coming from our first definition. So this concept that objects belonging to the same group should be similar to each other can now be realized by a term called compactness, and this concept is realized by separation. And here are different ways to measure it. You have variance, you have minimum pairwise, average pairwise distance or average central base distance to calculate compactness. And then you have pairwise again distances to measure the separation. Of course, there are some density-based ways to calculate compactness and separation, but still, I don't see any application for density-based measures. All the measures that you have here are somehow related to distance. It's still the basics, but not in this slide. I'm saying in general for clustering, you will not find anything better than distance. Some here and there you see measures related to density, but distance is the main measure. Approach to calculate the Sherrod coefficient. What it's trying to do is, it's trying to calculate the difference between average dissimilarity, which is captured by AI, and then BI is how good this point is with respect to nearby clusters. So let us say you have a clustering, you have a new clustering for the data. Then you're taking a point in the data, and then you're seeing how this point is different from other points in the same cluster. And this difference is measured by AI. And then you're taking the same point, and then you're seeing how this point is similar. You see the way it's presented? You see how this point is similar with other points in the other cluster. And that is captured by BI. This is the way to calculate BI. Once you have these two, then for each point you calculate what we call Sherrod measure, SR, Sherrod measure. And given this measure for each point, the average of these will be the mean Sherrod coefficient or the Sherrod index. This measure is always between -1 and 1 because of the way it is being framed. So now you know what it means by the value. If the value is very close to 1, the point is well clustered. If the value is very close to -1, then it is not very well clustered. So we are going to use this measure to come up with possible values for K, and then we are going to solve some examples. Okay, so this is the same notebook that we sent you.
We have sent you an email for those who are aware. If you did not receive the email, please let us know, or you have just came because we sent it to those who registered. Anyways, if you will give us your email, we'll send you again the email. You can go into the Google Drive and download the Jupyter Notebook you'll see. Who here knows how to use Jupyter Notebooks? Who doesn't know how to use Colab, Google Colab or Jupyter Notebooks? Who doesn't know how to use it? Does not. If you do not know it, no problem. Or we'll get someone to teach you how to do it. But tell us if you struggle, if you have any issues, just let us know. Okay? Now we'll send you the email. If you have registered for the workshop, you will have received the email. Open the notebook in your Jupyter, and you will find uh, these data with everything installed. Okay. Are you all set up for the exercise? Did you all receive the Jupyter notebooks? Excellent, David. Check your email. Uh, if you do not know how to use Google Cloud, let us know. It's easier for you to use it instead of trying to download them and then use them in Jupyter notebooks. Just raise your hand. Someone will reach to you and help you. We'll start right now with the exercise. Okay?
Okay, guys, so let's start. You have one Python notebook file, and then there are four data files. Those data files you can save it. The way I organized my work is I created a small folder, and then I place all the data files. So if this is not the case, just give the right path according to your setup. So in the first cell, I'm just reading the data. I have data in my data one txt file. I'm reading it and I'm displaying the part of the data. Usually, you should have some feeling of what the data is. One of the main reasons is sometimes you might have in the new data some names or some classes, and this might spoil your cluster. So you'd like to have a look at the data and see if the data is correct in the way that you need, and if it's not, then you do some data cleaning. But most of the practical data, you have to do data cleaning. You'll have some null values or NA values, and then you should know how to remove it. Sometimes you have categorical data, and for categorical data, there are many tricks. One hot encoding, or you have Bayesian encoding, and you have many types of encoding to get rid of categorical data. So on and so forth. So here I'm assuming the data is very nice, it's clean, and you have all real numbers. But in reality, no, you have these lots of missing values, you have categorical data, you have data which is not so straightforward. You can have some freeze inside the data. And you have to do all those pre-processing. So I'm assuming you know those things, or even if you don't know, we are just to use something simple. So here the data has two features, or two columns, and each row is a record. And this is a typical flat data. And once you have your data in this form, then you can use the algorithms right from the package. Since the data is in two dimensions, I can easily plot it. So I'm using here the package from Python and just plotting the data. Without even doing the clustering, you can tell what the clusters are. Which is something you can see, you can easily tell. So here I know that I have three clusters, three spherical, well-separated clusters. And then I'm using k-means to tell me the same answer. So that's the k-means algorithm from scikit-learn, or the way it's written sklearn. And if you have any algorithm from sklearn, it is more or less a standard implementation of the algorithm. To get your code into sklearn, you need to have a paper with almost 200 or more citations. So if your method is well known or well appreciated in the data analysis community, only then it will appear here. So if you have any method from sklearn as a reference and you can do better than that, that means you're doing an excellent job. So I'm getting k-means from here. K-means has many parameters to be frank. I'm just showing some, those I think the ones that we discussed in our discussion. So the first parameter, the number of clusters, the value of k. I'm giving the value 3. Now, that's a big catch. How do I know 3? Well, I don't, but I'm doing some small cheating here. I know there are 3 clusters, so I'm giving a value of 3. Maximum number of iterations. How long to do this? Given cluster centers, find assignment, find given assignment, find cluster centers. Well, I'm saying 10,000 iterations. And then those cluster centers that I throw randomly, well, I created in the slides something very nice. X very close to 1, 2, 5 very close to 1, and Z very close to 1. In reality, it may not be the case. So you have to come up with so many initializations. So here I'm saying I'm going to have 10 initializations. So I'm going to run the algorithm 10 times with 10 new initializations. And then the random state. This is something for repetition. If you give the same random state, you will have the same results on an average. And then I'm going to fit using this data that I have just read from the file. Once I'm done fitting the k-means model, then I have an output which is labels. So k-means dot labels underscore is nothing but the labels that the algorithm is giving me. And then I'm plotting the data and coloring it with labels. And then I'm also plotting the cluster centers. K-means dot cluster underscore centers underscore. That's the cluster centers I get from k-means. And that's the result when I run the algorithm. So you can change the parameters here and see how it will affect. For example, let me say instead of 3, I have 5 clusters. then this is what the K-means algorithm is going to do. But this is not correct, but you can see it's trying to come up with a cluster within a cluster. The reason is because I created 5 cluster segments. Similarly, you can have less number of iterations. For this small data, 5 is more than enough. Sorry, 1,000 is more than enough. But let me reduce the number of iterations. It's doing a good job even with 5 iterations. So maybe the data is so easy, it is able to match with 1 iteration as well. But in general, it's not the case. In general, the number of iterations may not be enough. You can take it from here or now. Now in this cell, we are seeing how we can estimate the value of k. So I'm getting a matrix from a scalar and I'm using the Shillot score. Okay. I'm assuming some values of k. For example, k can have any value from 2 to 8. This is my guess. The actual k could be in this guess or not. And then I'm just repeating this K-means algorithm. Every time I'm starting with a different guess for k. And I'm calculating the matrix score. The idea is, if the matrix score is maximum, then it is very good cluster. And the maximum value you can get is 1. So using this loop, I'm just plotting for different values of k, what will be the score. And that graph is eventually at the bottom. So this is the graph that you get what once it should be as a code. This is the famous elbow graph. Typically in this graph, if your initial guess was correct, you will find like something like an elbow. Like there is a peak and then it keeps falling down. And that peak usually will tell you what is the best number for k. Here because the data is so nice, you can see that this peak is very obvious. But later on you will see when the data gets complicated, the peak is not so obvious. So I'm using another data now. This is data, this is famous data again. This actually is from a paper. It's called as compound data. In this data, you also have class labels. I'm deleting the class labels by this line row here. I'm removing the class labels. And now I'm doing the same thing. Without looking at the data, I'm using the same process. And then this is the graph. This is the elbow graph. And I don't see any clear elbow. It is hinting me at least that there are maybe here from 5 clusters. But it also is saying me that maybe 2 is the best number of clusters. And this is what will happen. If you take a real data and do draw the elbow graph, k versus Shillot index, you'll see that it will not be as clear as before. Now what should be the value of k? Should we take 2 or should we take 5? Any guess? So let us say I take the value equals to 2 because that's the max. And that's what I'm doing here. I'm getting the best k as the max, blind. Okay. And then we will run the k means with two number of clusters, and then let us draw it and see what happens. So you draw it and you see something like this. So that was how the data was looking. And of course, this is a two-dimensional data, and it looks weird, but you will have a data in dimension in real world. It will be completely far from your imagination. And now you can see why K-means was struggling. Because the data doesn't know K-means. The data doesn't know what K means. Data is just data. It's coming from some system. And K means was assuming some spherical clusters and using distances to calculate the compactness and separation. But here data doesn't know what you mean. So here you have clusters in various shapes. You have a cluster here, a cluster here, a cluster here, so on and so forth. So how many clusters do you see in this data? So now you see our brain, which was master in clustering, is also struggling to tell the answer. But our brain is doing something. It is somehow trying to say that this is one cluster, this one cluster, this is one cluster, and this one cluster. Something is trying to do. What it's trying to do actually is trying to look at the points which are dense, which are close, and trying to make this as a cluster. This idea is realized by DB scan. It's a density-based clustering method. And we will see that maybe after Salah or depending on the organizer.
Now we'll take a break, 10 minutes. There's food, there's coffee, there's water. Just relax and we'll come back, continue with the workshop in 10 minutes, okay?